There, polar bears. So today's lesson will be on Newton's second law. Newton's second law says force is equal to mass times acceleration. So what I'd like to do is go over a few forces, understand them, and use some examples so that we can look deeper into our world of pole dancing from a physics point of view. Okay, so let's look at some forces. Let's go back to the rock. The rock experienced gravity and the normal force. Let's go back to the shopping cart. And that experienced friction. Let's look at some other forces. So, many of us are travelers, so let's imagine this is a plane. And the plane is flying, and you've heard of like headwind or tailwind. So that's air resistance, the fact that it has to cut through air. Okay, so air resistance. Then there's spring force. So if you push down on a string, it will push you back up. Okay, so that's spring force. Then my favorite is tension. So let's imagine this is a tetherball court, and you hit the tetherball, and the force applied by the string is tension. Another force is applied force. So let's imagine that's my hand, push a cup off of a table. So I'm going to apply a force, so this is applied force, and the cup will fall. Now the cup will fall this way because of gravity, but okay, so this is applied force. Me pushing the cup is applied force. Let's review. We have gravity, we have normal force, we have friction, air resistance, spring, tension, and applied. These are all forces. Let's take a look at Newton's second law. It says force is equal to mass times acceleration. Force is a vector, so is acceleration. What is a vector? A vector just means it has a value, like a numerical value, known as a magnitude, and a direction. So that's the special part of a vector, is that there is a direction. So let's say a car is going, you push the gas, and you start to accelerate at some rate, let's say 10 meters per second. Okay, so that means there is a direction that you're going and there is a numerical value. So that is what a vector describes, magnitude and direction. Newton decided that mass, kilograms, and acceleration, which is meters per second squared, is equal to a Newton. Okay, Newton, we love you, we remember you forever. So a kilogram meter per second squared is a Newton. A Newton is the unit used to describe a force. Now let's take a look at tension. Illustrated here, you see me spinning around the pole, and you see our tetherball example. So, what do we have in the tetherball example? We have the force here, which is tension. Okay, and the ball, once it's hit, will go in a circular path. So, same thing for us. As soon as we take off, we're going into our spin, we're going into a circular path. So we must also be experiencing tension between these 2 points. So, these are my arms. That is what is supplying the tension. Now, what is centripetal force? We hear about this all the time. Centripetal force is nothing more than an adjective. It's a descriptive term. So in other words, let's imagine the rope wasn't here. There is no tension. You hit this tetherball or this ball, and it would just go straight if this didn't exist. So centripetal force is being supplied by tension because that is what's forcing it to go in a circular motion. So centripetal force is not a new force. It is a descriptive term that says an object is forced to go in a circle. Okay, so if it's forcing it to go in a circle, it's centripetal force. Centripetal force in this case is supplied by tension. In this case, it is also supplied by tension between our shoulder and our hand. Deeper look into this. Let's be the tetherball. Okay, so let's imagine you were standing here and you were holding this rope. Would you be pushing or would you be pulling this rope? Let's just imagine it. You have some weight at the end of it. It's going a circular path. Would you be pushing or pulling? Oh, pulling. Good job. This is a pulling force. Okay, so what about if you were the ball, which we usually are? Let's just imagine. That's the ball. Okay, if you are here, would you be pushing the rope or would you be pulling the rope? Good job, pulling. So this case of centripetal force is a pull force, not a push force. I know what many of you are thinking. Oh, I thought it was a push-pull. Well, let's go back to the rock. So the rock had gravity and the normal force working in opposite directions. And what did that rock do? It didn't do anything. It stood still. So let's look at if we did one pull and one push. These would also cancel each other out, putting you at 0 newtons, which means 0 force, which means 0 spin. Boo. Now, I'm not saying that we never should push. There are times when we want to do a push-pull, like when you want to do a bracket up on the pole and you want to stay still and do like an airwalk. That's when you push-pull. When you want to slow yourself down, when you want to stop. If you want a small amount of float, those are times to use a push. But if you really want to spin and experience that centripetal force, then you have to pull and apply tension. So strengthen those shoulders, loosen that grip, and feel the force. Let the force be with you. So here's the quiz. What is supplying the centripetal force when you do a spin?